Okay, everyone, so here we're going to be talking about short circuits, so please do copy down as I go through. So we're going to be talking about short circuits and also electrical safety and what are some safeguards in electrical panels and such, okay? So I'm actually taking this from the textbook, page 462. I also just recommend that you just read through all of 11.3 just to get an overall view. So it's Ohm's law and then also things like electrical safety, okay? As mentioned, the textbook, the specific parts of the textbook that I want you to read, you can find it under content. Sorry, this must be getting so boring. Unit 1, electricity, chapter 11, current electricity, under these notes here, and then it has 11.3 textbook right over here, okay? You'll also notice that the questions are also the homework questions. If you're able to get to them, there's some homework questions on the last page of that PDF, okay, on page 467 there, okay? So that's available. It's already posted. A short list of just 11.3 is posted there. Okay, so let's go on and talk about short circuits, okay? So maybe I don't know if this is worse or better. Okay, anyways, I'm going to do this, okay? So a short circuit is an accidental low resistance connection between 2 points in a circuit, okay? And it causes excess current flow, okay? So what actually happens is that there's a wire, for example, and let's just say you connect a wire with nothing using up the electricity. So for example, a direct connection between the positive end of a battery and the negative end of a battery, that will cause a short circuit. So this excess flow can cause overheating and also fire. Okay, so sometimes what happens is that a power line is knocked down in a storm, and then if there's torn wires that no longer provide a complete path or circuit for electrons to flow, what happens is that you might become the conductor. Let's just say you touch the wires because they're now knocked down and they're live wires. You become the path, and let's just say if you have two of your hands and then you touch, for example, okay, or even if the water is conductive because it's a semiconductor because of dissolved minerals in it, okay, then what will happen is that the electricity will use your body as a path to the ground, okay. Another thing is that sometimes a technician may want to create a short circuit intentionally so that they can work on a device without interrupting the rest of the circuit. That means that they want to actually purposely allow the current to kind of go crazy so that they can work on this other higher resistance area, because electrons will go with the path of least resistance. They will go with the open wire loop rather than the resistive loop, and then that way it leaves them kind of safe, okay? Please copy this down. I have posted the notes under the same folder, okay? So don't worry if you're not catching up. You can always catch up by looking at the notes as well, okay? Let me just show you these two videos while we're watching. I have a feeling the volume won't be on.
This revolutionary new device can remove up to 10 times more earwax than a traditional cotton swab.
Okay, so right over here, don't try this, okay? But look how easy it is. Okay, steel wool is very, very thin. Please don't try this at home. Maybe I shouldn't even show this. Okay, I'm going to stop showing this. Okay, oh my goodness. And so you can imagine that sometimes if there's, okay, nothing. I'm not even going to say anything. Yeah, okay. So that's that right there. And I'm going to show you a short circuit with a fuse, okay, as well. So let me just show this to you first. So
Make Magazine's electronics course, written by Charles Platt.
What's happening here is...
Experiment 2. Let's abuse a battery.
This person...
Create this short simply by touching the two ends of the battery together.
This person
we are essentially creating electrical current buildup inside the battery.
This person is purposely connecting the wires together without any load. So notice that there's no motor, there's no flashlight, there's no lights or anything. Okay, so what ends up happening is that the current actually goes through, the wires become very, very hot. If this was a higher amperage or higher voltage, this thing might actually catch on fire, okay? But because AA batteries are very quite low, okay, on the scale. Basically, what's happening here is all that's happening is that the battery is actually getting destroyed, okay?
How do we stop short circuits?
What would you do to stop a short circuit? So sometimes what will happen is, rather than as a safety guard, this is called a fuse right over here, and I'll show you a better picture of it. But there's a small metal S in here. Usually it's made of tungsten or tin, okay? And so rather than directly connecting the wires to the battery, okay? Instead, if we put it in a fuse instead, what will happen is that rather than the current being overloaded and creating a short circuit, what you'll notice that there was a small spark right there, okay? This low resistance, it has a very low melting point comparatively. If you saw that little spark, that's actually the fuse blowing, and what's happened is that the metal has actually melted and it's now been destroyed, and then that circuit can no longer be completed. Okay, so that's like a safety feature. I remember in my old house growing up, now electrical panels, you just have circuit breakers, and I'm going to talk about that in another video. But circuit breakers, you just flip the switch back and forth. But in older houses, or when I was growing up in like the 80s, we used to have fuses. They were like glass knobs, and it was in a fuse box. And then inside would be either metal, a metal such as tin or tungsten. It had again a lower melting point so that it would break if the current was too high, it would melt it, and then it would break the circuit. And then I remember we would have to like undo it, go to Home Hardware, buy another fuse that was compatible, and put a new one in. And it would be blackened because the fuse had blown or had melted. Okay. The annoying thing about fuses is that, so I'm just going to keep going with this. Okay, so I'm sorry, I'm just going to like go over to here, okay? What's annoying about fuses is that you have to replace them, okay? Because they get destroyed, okay? So electrical safety, be sure to unplug electrical devices before you handle them. Certain devices maintain a charge even when they're unplugged, so there's kind of like a background charge going on. The circuit is still running, okay? And then fuses and circuit breaks. A fuse is a safety device that has a metallic conductor with a low melting point. As I mentioned, it's very often SN, which is tin, okay? Or it might be W, which is tungsten. These are just the chemical symbols, okay, on the periodic table. It has a very low melting point. This means that if the current gets too high, okay, for example, if there's a short circuit and the temperature gets too hot, the fuse melts, and then the current stops, and it prevents further problems, okay? So blown fuses must be physically replaced because they only work once. And then this is the electrical symbol for a fuse. It's a little squiggle. We don't see this very much, to be honest, in grade 9, but I just want you to know about it, okay? Let me just show you a picture of that. So here is another example of fuses. Some fuses look like this, so it would be connected to the circuit like this. Over here, these are the thin metal wires that are still intact. And then after this wire has melted, the fuse is blown. Okay, so I'm just going to watch this video as well, really quickly, hopefully. An ad, sorry. Okay, I'm just going to show this to you. I think it's at 2 or 3 minutes.
Red, simply because there's so much amperage.
Okay, so right over here.
Simply because there's so much amperage.
So lots of amperage going through, and it actually blows the fuse.
But what that whole thing does is turn red, simply because there's so much amperage.
There's too much amperage, too much current, that it actually melts it, okay? That's an example right there. Okay, let me just see what else I want to show you, okay? Let me just show you a circuit breaker as well, okay? So we'll talk about circuit breakers next. So let's just go here. So a circuit breaker does the exact same job, except the wire inside does not melt, okay? So circuit breakers are more modern. Circuit breakers are what you have in your electrical panel at home or in your condos or whatever, okay? So instead of the wire melting, what happens is it actually heats up. So there's two strips of metal, two different types of metal that are kind of bonded together, but because they have different heat points, one of them bends at a different rate, and it triggers a spring mechanism that turns off the flow of electricity. So once the breaker cools down, you can actually just reset it. So a lot of times, let's just say I plug in the toaster and I plug in my microwave accidentally. They both draw a lot of amperage. When I do that on the same panel, it's drawing too much. I don't want there to be any, I don't want there to be too much current going through, because that's very dangerous. Then it will actually blow the circuit breaker because it heats up too much, okay? So older buildings tend to have fuses, more modern buildings have circuit breakers. Side note, why might that be? It's because fuses are very, very inconvenient to replace. You actually have to go back and you have to go and buy more, okay? So please copy those down, and let me just show you a picture of a circuit breaker, okay? And maybe also a video. Yeah, okay, so trips that end 1 minute. Okay, so I'm just gonna show you the video first so that we kind of understand what's going on. So over here, there's a 5 amp current going through here, which is actually quite high. So it's going through here. What you'll notice that this is called a bimetallic strip right over here. There's actually two fused pieces of metal with different heating points, or they expand at different rates. And then what will happen is that this curvature will actually pop as one of them heats up, and then it will trigger the opening of the circuit. And then this would be like where you press to turn your circuit breaker on and off. Okay, so let's just wait for it. There we go. So it just triggered it. You'll notice that now that this has been like look at the curvature of this of the breaker of the metal right over here versus right over, let's just say like right over here, right? So notice that it's curved right over here, whereas after the fact, it is no longer curved. Okay, it's kind of a different shape, and it just triggers that spring mechanism and it pops the circuit open. Okay, when it pops the circuit open, it's like an open switch, and then the current no longer flows through. Okay, so I'm just highlighting over here. It's really difficult to see, but it's a curved item right here, whereas over here it's curved in a different direction, concave versus convex. Okay, so that's like the concepts behind that. Okay, there's a few more safety items here. Okay, so there's also, for example, a 3-prong plug. So the third prong on an electrical plug connects the device to the ground wire of a building, and it sends the unwanted flow to the ground and not into a person by accident. Because if you were to, for example, touch and then create a circuit, if there is too much current flowing through, you can get electrocuted, but instead it sends the unwanted flow to the ground because it's actually connected to the ground. And I just literally mean like those, you know, let me just show you. Okay, I don't have an example. Anyways, you know the plugs, right? The plugs that are like in everything, that draws a little bit more amperage. It's the third bottom plug right there, okay? There's also GFCIs. GFCIs are ground fault circuit interrupters, and they detect changes in current, and it opens the circuit, stopping the current flow, and it stops the electrocution. The GFCIs are the ones where you find them sometimes in bathrooms. So let me just look that up. GFCI. Okay, like these types. Okay, so anyways, this is like a 3-prong plug right over here. But the GFCIs, they often put this in bathrooms or by water, just because it'll trip up the circuit. It prevents electrocution because of water. And you actually, like when you trip it, you actually have to reset it by pressing the button. Okay, so that's a GFCI. Okay? Okay, so I would say that if you did not finish up the Ohm's Law problem, so you know how we had this yesterday, or yeah, whatever, okay, in the previous lesson, if you haven't finished up these 8 problems, please finish them up now. And then otherwise, if you're pretty good and you have all these notes down, the rest of the class can be used to complete the homework questions that are listed here on page 467. And again, I've already posted the textbook right over here, okay? So it's under today's date, okay? Under Brightspace, okay? So you have the rest of the period just to do work, okay, or catch up on other work. And then I'll see you the next day.